Let's go over section 1.4, matrix algebra. In this section, we're going to talk about some properties that we know from real numbers and complex numbers we've learned in school, and we're going to see if those properties hold for matrices as well. So from past experience with real numbers and complex numbers, we know that if A, B, and C are just some real numbers or complex numbers, that if you add A with B, it's the same thing as adding B with A. For example, 3.2 plus 7, well, that's 10.2, but that's equal to 7 plus 3.2. It doesn't matter the order of A and B, you're still going to get the same answer. Well, what if you have two matrices, A and B? If you add them, is that going to be equal to B plus A? Well, the only way we can add two matrices is if they have the same size. So first off, we have to specify the size. So A is an m by n matrix. That will force B to be an m by n matrix in order for us to add them. And it is true, if you take a matrix A and add it to matrix B, then it's going to be the same thing as taking the matrix B and adding it to matrix A. You can do a proof of this, but I give you a little proof here. So A plus B is Aij plus Bij, but that's the same thing as Bij plus Aij. It doesn't matter the order inside the entry, so then this is B plus A. Let me give you an example that will maybe clarify this. If A is the matrix 3, 1, 2, 4, and you add to it 0, 9, 5, negative 3. Adding these, you get 3 plus 0, 1 plus 9, 2 plus 5, 4 plus a negative 3. Exactly what I have here. Aij plus Bij. But then I can switch the order. So this is equal to 0 plus 3, 5 plus 2, 9 plus 1, and negative 3 plus 4. So just rewriting these, because that's the property we have with real numbers, and then we can split it like this. So this is equal to 0, 9, 5, negative 3, plus 3, 1, 2, 4. So how we add matrices, that doesn't matter. Matrices are commutative. The second property I want to talk about is with real numbers we know that they're associative when it comes to addition. So if we have three numbers A, B, and C and we want to add them, if we add A and B first and then add C, it's the same thing as adding B and C first and then adding A. That also holds for matrices. So if we have A, B, and C as matrices, well, we can add A and B first and then add C, and that's the same thing as adding B and C first and then adding A. And you don't have to put this m by n here each time. I'm just doing that because in order for us to add these matrices, they have to be the same size. So I just want to bring your attention to the fact that they are all the same size. So this is true, and you can also prove this, and the proof is I think in the book as well. Okay, the next thing I want to ask is, does the property, or we have commutativity of multiplication, does that hold for matrices? So we know with real numbers something like 3 times 5 is the same thing as 5 times 3. Is it true that A times B is equal to B times A? Well, the answer is no. First off, sometimes you can't even multiply. If you can multiply A times B, that doesn't mean you can multiply B with A. For example, if A is a 2 by 3 matrix and B is a 3 by 5 matrix, well, you can multiply them because you have this 3 and this 3 here, cancel out, and you get a matrix C, which is 2 by 5. But if you try to multiply B, which is 3 by 5, by A, which is 2 by 3, well, these numbers are not the same. So this does not exist. So it's possible to multiply two matrices, but not be like to multiply A with B, but not to be able to find B with A. However, if the matrices are square, you can multiply them. So what if A and B are both n by n? Let's say they're square matrices. Does this property hold? Well, the answer is no. And let me give you an example. So let's say A is the matrix 1, 1, 1, 1. And let's say B is the matrix 1, 1, negative 1, negative 1. Let's multiply A with B. So A times B is 1, 1, 1, 1 times 1, 1, negative 1, negative 1. Well, we get, for the first entry, 1 minus 1, that's 0. 1 times 1, that's also 0. Then the next one is this times this. 1 plus negative 1, this is 0. And then the last one is also 0. Okay. Now let's find B times A. And let's make this smaller so I can fit it on the screen. Okay. So now B times A is 1, 1, negative 1, negative 1 times 1, 1, 1, 1, which is, okay, we're going to take this one with this one. That's 1 plus 1, 2. And then you could finish this, but you don't have to because it's already not going to be equal. But you'll see that you get 2, negative 2, negative 2. And remember, for two matrices to be equal, they have to be the same size, and they also have to have the same entries. Here I have 0, 0, 0, 0. Here I have 2, 2, negative 2, negative 2. These are obviously not the same matrices. So here I've shown you that I have two matrices, and I can actually define A times B and B times A, but they are not equal. So matrices are not commutative under multiplication. So let's write that in red. Under multiplication. So that's really important. Okay, so here's one rule that we broke. Are there other rules? Well, we have this rule that with real numbers, if we take one real number and multiply it by another real number and we get 0, then at least one of them has to be 0. Does this rule hold for matrices? So if A times B is a 0 matrix, so let's say this is m by n, let's say B is n by p, and this one is a m by p matrix, which a 0 m by p matrix is just a matrix that has a bunch of zeros, but it has m rows and p columns. Does this force one of these matrices to be 0? And the answer is no. We just saw an example of this up here when we did A times B, where we had this matrix 1, 1, 1, 1 and 1, 1, negative 1, negative 1. We had two matrices that when we multiply them together, we got a 0 matrix. And neither of A or B is a 0 matrix. So this does not hold. So you can see that there's some properties that you can take from the real numbers and extend it to matrices, but some properties don't work. So what can we assume? So what properties hold for matrices? I'm going to give you a list of properties that hold, and then we're going to summarize them. And these properties are listed in your book. They're on page 47. So you don't have to copy them down. You can just open your book and look at them. So let's just talk about them real quick. So matrices are commutative when it comes to addition. A plus B is B plus A. They're also associative when it comes to addition. Okay. They are associative when it comes to multiplication. So if you multiply A times B and then multiply it with C, that's the same thing as multiplying B with C and then multiplying with A. Notice for rule 3, I didn't change the order of any of the matrices, I just moved the parentheses around. The fourth property is that if you add two matrices together, assuming that you can add them, and then multiply by a matrix A, you can distribute this matrix A. You can put it in front of the B and in front of the C, just like the distributive property with addition in real numbers. Here you can also distribute in the back. You see you have A plus B. Well, you can send the C to everything, but you keep it in the back. Okay? Here I have alpha and beta, they're scalars. Well, if we take two scalars and multiply them together and then send them into A, it's the same thing as just taking one of the scalars first, multiplying it with A, and then multiplying by the second scalar, just as you would expect. And if we have two matrices, A times B, and we multiply their product with a scalar, then we could send this scalar into the first matrix A and then multiply it with B, or we could send the scalar into B and then multiply with A. That's fine. And the last two rules involve like the distributive property. Here, if we're adding two scalars and then multiplying that with the matrix A, you can just send in that scalar to the matrix A and add them. So both of these scalars. And if you're adding two matrices and then you multiply by a scalar, instead you can multiply both of the matrices by the scalar and then add them. So a lot of these rules are pretty straightforward. The thing I want you to notice about all of these rules is that I never switched matrices around when it came to multiplication. See, like this one here with associativity, the matrices stayed in the same order. When I distributed this A to this B and this C, like right here, the A stayed in the front. I didn't ever put it in the back. When you distribute the C stays in the back. You can see I don't switch the orders at any time. Now these are scalars, so it doesn't really matter the order here. Okay, so in summary, I want to say that you want to be careful with multiplication. Never switch the order of matrices when you have multiplication. All other rules are basically the same. So whenever you want to add matrices or you want to figure out a formula involving matrices, unless you have multiplication, you can do basically anything you've seen before with real numbers. Just be really careful with multiplication. All right, we're going to have some properties of the transpose. So let's recall what it means for a matrix to have a transpose. Every matrix has a transpose. If you have an m by n matrix, the matrix given by lowercase aij, the transpose is just putting in the ijth entry the jith entry. Okay, and this is an n by m matrix. So we have some properties that we need to know, and you should memorize these properties for tests, and for your homework you should get a lot of experience with them. Some of them are straightforward. The first three are straightforward, and the last one might be the only thing that you wouldn't think would happen. So the first one is that if you take the transpose of a matrix and then take the transpose of that, you actually get the original matrix. That makes sense, right? You take a matrix, you flip it along the diagonal, and then you flip it again. You should get the same matrix. So that one's pretty obvious. The second property of transposes is if you have a scalar and you multiply it with a matrix here, then you take the transpose. Well, that's the same thing as taking the transpose of the matrix and then multiplying it with the scalar. Okay, so let me actually give you an example of this one, just so we're clear. You can see that this one is pretty obvious too. So if we have 2 times this matrix, 3, 1, 1, 7, and I want to take the transpose, well, I'm going to send 2 into everything, and then I'm going to flip it. So this is 6, 2, 2, 14. Then I take the transpose, and I get, well, this one happens to be symmetric, but it doesn't have to be symmetric. You can use any matrix. But then I could, instead, I could just take this matrix, take the transpose, and then multiply it by 2. So if I take the transpose of this, I get 3, 1, 1, 7, and then send in that 2. I'm going to get the same thing here. So I get 6, 2, 2, 14, and you can see that these two are equal. So let's see what the difference is. Here I put in the 2 with this matrix, then took the transpose. For this part, I took the transpose first and then multiplied it by 2. So that's what I have here. Now this is just an example. It's not a proof of this. The proof would be in the book if you want to look at that. Okay, the next property is that the transpose of the sum of 2 matrices is actually equal to the sum of the transpose of both of the matrices. So the transpose distributes when it comes to sums, okay? So it's like sending in this transpose, so this A and this B. Now the last property, which is actually not obvious, is that A times B, if we have 2 matrices and we multiply them and we want to take the transpose, this is the same thing as taking the transpose of the one in the back and then multiplying it with the transpose of the one in the front. So it's not A transpose times B transpose, it's B transpose times A transpose. Be careful with that. Okay. We're going to do actually an example of this number 4 here. So let's say we have these 2 by 2 matrices A and B. I want to find 3 things. I want to figure out what A times B transpose is. And I want to verify that A times B transpose is B transpose times A transpose. So I want to show that this is actually true. And at the same time, I want to show, for this case, A times B transpose is not equal to A transpose times B transpose. What we would think would happen doesn't work for this example. But it will work, this one will work, which it'll work for every example you can find. Okay? So let's start by finding A times B transpose. So let's put that down here. A times B transpose means that I need to multiply A and B first. That's what parentheses mean. And then I want to take the transpose. So let's find A times B, which is 1, 2, 3, 4, times the matrix 4, 3, negative 2, 4. Okay. Okay. By now you should be good at multiplying matrices, so I'm not going to go through it in a lot of detail. We're going to get 4 minus 4, 3 plus 8, 12 minus 8, and then 9 plus 16. So A times B is 0, 12, 4, 25. This is 11, not 12. 11. Okay, now let's take the transpose of this. So AB transpose, in parentheses, that is going to be 0, 4, 11, 25. We flip along the diagonal. Okay, so we've found this. Let's copy it. Let's copy. I'm going to put that down here. Okay, let's put it in blue. Now, what I wanted to do was first I want to verify that this is equal to B transpose times A transpose. Okay, so let's find B transpose, and then let's find A transpose, and then multiply them together. So recall that actually I think what I'm going to do is I'm going to erase this so I can see up here. Just so we can see the original problem. So I'm going to move this back up. And then I'm going to move this up. Put it up right here. Okay, so B was 4, 3, negative 2, 4. So take the transpose of that, we should get 4, negative 2, 3, 4. So let's write that down. 4, negative 2, 3, 4. And now let's take A and find the transpose. So we should have 1, 3, 2, 4. And now we want to show that B transpose times A transpose is equal to this. So let's see if that's true. B transpose times A transpose is 4, negative 2, 3, 4. Times 1, 3, 2, 4, which is, okay, so this is 4 times 1 minus 4, which is 0. 12 minus 8, no, sorry, this is 12, 12 minus 8, then 3 plus 8, and then 9 plus 16, which is equal to 0, 4, 11, 25. Is that what we had for A times B transpose? It is 0, 4, 11, 25. So let's delete this and move this one up here. Okay. So we've shown that this is actually true. Let's show that this one's not true. So I'm going to just take A transpose and multiply it with B transpose and see what I get. So maybe we'll do this in green. So A transpose times B transpose is 1, 3, 2, 4, 4, negative 2, 3, 4. Okay, so we get 4 plus 9. And we could probably stop there, but I'm going to continue because if we don't get the same thing as this, then we're done, and we don't. But anyway, I'll continue it just to do that. So negative 2 plus 12, 8 plus 12, and then I get negative 4 plus 16. This should be 13, 10, 20, 12. Yeah. So this is our answer. Get rid of this stuff. Put this here. And you can see that this is not equal to AB transpose. 0, 4, 11, 25, we don't have that. So we checked this one as well. This is not equal. So be very careful with this. You need to memorize this, that A times B transpose is B transpose times A transpose. Okay, let's move on. I just have a couple more things I want to talk about. The first thing is something called the identity matrix. The identity matrix is a square matrix. Notice that I have n by n, and we call this matrix I. So if you see the letter I, the capital I, you're always going to think of this identity matrix. And this matrix is equal to delta ij, where delta ij is equal to 1 or 0, and it's 1 if I is equal to j, and it's 0 if I is not equal to j. So let me give you an example of what I mean. The identity matrix that's 2 by 2 is going to be 1, 0, 0, 1. You can see that this is the 1, 1 entry, and this is the 2, 2 entry. That means 1, 1, I is equal to j, and 2, 2, I is equal to j, so we put a 1 there. This is the 1, 2 entry, so 1 is not equal to 2, so I put 0. This is the 2, 1 entry, and 2 is not equal to 1, so put 0 there. The 3 by 3 identity matrix looks like this. And you could go on. You could say the n by n identity matrix has n ones along the diagonal and zeros everywhere else. Okay. Here's a nice fact. The identity matrix commutes with any n by n matrix when it comes to multiplication. So if you have A, that's an n by n matrix, A times I is going to be equal to I times A. Remember, in general, if we have a matrix B, A times B is not equal to B times A. But when it comes to the identity matrix, this is always true. You can take any square matrix. A times the identity is always equal to I times the original matrix. So yeah, the identity times A. Okay. And finally, we're going to talk just a minute, very briefly, on invertible matrices. So we call a matrix that's square. Notice that this is a square matrix, n by n. It's invertible. I'm going to actually put this here. So we want to make sure that it's square. A matrix is invertible if there exists another square matrix, so a matrix B, which is square, so it's n by n, such that A times B is equal to B times A. So these two matrices commute, and they're actually equal to the n by n identity matrix. Okay? So it's sort of like what you think about when you think about an inverse of a number. So like 3 times 1/3 is equal to 1. This is like a 1 by 1 matrix. This is a 1 by 1 matrix, and they give us the 1 by 1 identity matrix. That's kind of like what we're thinking about when it comes to just a regular square matrix. So we're thinking of something that when we multiply it by its inverse, we get the identity. Okay. But there's no division when we're talking about matrices. We don't do 1 over a matrix. Okay. So That's something I also want to just throw in here. B is called the inverse of A, and we usually write the inverse as A to the negative 1. Now this does not mean 1 divided by A, because when it comes to matrices we have nothing, do not have division, but we do write A to the power negative 1 to represent that it's the inverse. Okay. So let's do a quick example of this, and then we'll talk more about this in the next section. So let's show that these two matrices are inverses. That means that this matrix A, and let's call this matrix B, that A times B is equal to B times A, and what we're going to get when we multiply them is the 3 by 3 identity matrix, which is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Let's show it. Okay, I'm just going to copy these. I'm going to put them down here. Paste. Oops. There we go. So let's multiply them. So I'm going to do A times B first. Okay. So here I'm multiplying A with B. What will we get? First entry, this row times this one. We're just going to get 1 times 1, which is 1. Okay. Then continue this row with this one. We're going to get negative 2 plus 2, which is 0. This row with this one, we get 5 minus 8 plus 3. This is also 0. And then just continue this process. So now we're going to do the second row, this one. You'll see that we get 0. Then with this column, we're going to get just 1. With the last column, we're going to get negative 4 and a 4, that makes 0. Okay. And then let's do the last row with the first column. This is going to be 0. Then with this one, 0, 0, 0. And then the last one, we just get 1. So this becomes 0. And we get the 3 by 3 identity matrix, which is I. Now, I'm not going to do this. You can multiply this matrix with this one. You should also get I. That's a good exercise for you. But you'll see that these two matrices are inverses of each other. So A inverse is this matrix B, and you could also say that B inverse is this matrix A.